wer von euch hat schon mal oder weiß, was Citra ist? Okay. Wer von euch weiß, was Dolphin ist? Okay, das ist weniger als, mehr als ich gehofft hatte. Gut, nur mal so nebenbei, wir haben einen der Initiatoren der Projekte hier. Und er beschäftigt sich gerade auch noch zusätzlich mit FEX, was ja die Abstraktionslayer oder Emulationslayer quasi ist zwischen x86 und ARM und wird jetzt gleich hoffentlich sagen, was so alles ganz toll ist dabei, wenn man sich damit beschäftigt. Viel Spaß!
Yeah, hi, so the moderation was in German, but the talk will be in English. I hope that was clear from the description, so apology if that's a problem. But yeah, we'll be talking a little bit about x86 on ARM emulation today. There will even be a demo, and the demo has always failed spectacularly in different ways, but they are all entertaining, and I'm very curious to see how it will fail today. But yeah, I wanted to give a quick introduction about who's even talking to you. My short pitch is always I'm a tinkerer turned quantum physicist turned software engineer, and you will see why in just about a minute. I started getting into all of these emulation things when I learned about video game console emulators. So we already mentioned Dolphin before. That was probably one of the first projects that I got in touch with just as a personal user. I was very avid, I had a physical GameCube at home and I loved playing Super Smash Bros. And when I learned about tools existing that allow you to play these video games on a system, on a regular PC, that these games were never designed to be played on, I was completely blown away by how could this even be possible. And it really, really pushed me to learn about how these things work, because it was so incredible to me that I wanted to just do anything to understand how that functions. And yeah, one thing led to another, and I ended up being part of the core development team of that emulator, and eventually others followed, also as mentioned in the introduction. None of this was meant to be my day job. I actually ended up studying physics, did a couple of fun things. As I mentioned, I wrote my thesis in quantum physics, so lots of fun things to have to do there. Here are some pretty pictures, but yeah, come find me later if you're interested in details. My first day job after uni was actually back in software engineering, though, because as it turns out, if you want to make a living out of quantum gravity, it doesn't work so well. Whereas software engineering, it's a pretty cool challenge, and you can actually pay the bills using it. My first job after uni was at Imagination Technologies, where I worked on the PowerVR driver, and later one thing led to another. I also happened to work on I got the opportunity to work on the AMD Radeon driver that is shipping in Mesa. So it was all open source at that point. Really, really nice opportunity. And now, through one way or another, I ended up working on x86 on ARM emulation. And yeah, so, if you want to follow me and read more about this stuff, you can follow me on Mastodon. But yeah, we're going to talk about FEX. And just a quick clarification, because I know we have a couple of train nerds around here. It's not that one. We're talking about FEX-Emul, an open source x86 on ARM emulator. We are on GitHub. We are a Linux-specific project because, as you might know, on macOS there's already Rosetta, whereas on Microsoft's platforms there is already a project called Prism. So the proprietary platforms already have their vendor-provided solutions, whereas we are the ones filling the gap for Linux. So we have an open source compatibility platform for a new laptop and other consumer hardware that promises to have longer battery life than your regular x86 devices. So this one in particular, a Lenovo X13S, is an ARM laptop. It's a pretty nice experience. It's a bit pricey for what it is. But the key thing for me as a user I always found impressive was that these devices can get away without a fan, which is such a mundane thing, but it really makes a difference in terms of the user experience because you can do really heavy work. and it just doesn't like spin up or something. So I don't know, maybe that's just me, but I value that a lot. But still, we want a solution to actually keep using our proprietary software, and FEX provides one building block for that. We actually had our 7-year anniversary the other day, which might be surprising because I think it's a relatively unknown project, maybe because few people actually run ARM laptops in the wild today, and if they do, probably not Linux. So yeah, we've been able to get under the radar of most people for 7 years, but as we'll might notice later, that's probably going to change soon. Yeah. Right, so just to give you a general understanding about the problem that like the scope of the problem that we're solving, when I say x86 on ARM emulation, it's not just a simple one-to-one mapping, but I like to describe it to my normie friends in a way that you would talk about general translation from German to French, German to English, whatever. You have two speakers of their respective foreign languages, their respective native languages, and you have a third person on the side who needs to translate what one person says to the other on the fly. On the fly, so that they can still have the conversation even when they don't speak the other language. And you might imagine, like, depending on what you're talking about, where's the train station, where can I grab some food, these simple issues, you can get by with very, very simple means. You just need to basically communicate using the bare essentials. That's the simple stuff. And similarly, with x86 and ARM emulation, you could do like the bare minimum to get simple applications running as a proof of concept, and it would be all fine. But what you really want is you want to have a very advanced understanding of the language. So when they talk about society, big political issues, that kind of thing, where nuances really start to matter, that's the part where you both need the vocabulary to understand what the speakers respectively are talking about, and you also need the finesse to really accurately capture the intent and map that to the target language in this very precise manner, so that miscommunication doesn't happen just as part of the translation. And this is exactly what we do with FEX. We are really not just trying to be a proof of concept, but really something people can use on whatever application they want. We want to be highly compatible with as many applications as possible. And at the same time, we want to be able to do this at extremely high performance, so that even things like gaming is possible without, we want to be competitive with x86 laptops. So naturally, we want to be accurate and fast wherever possible. And so to get a little bit more technical about this, I've prepared a little diagram for this. But basically, the stack that we're looking at the very bottom is we have the hardware, the x86 CPU that's running the game's instruction. The game sits at on top of the CPU, we have the software gradually stacking up, and the lowest level here is the Linux kernel itself, the operating system that provides abstractions like a memory management, multi-threading, inter-process communication, like GPU access, for example, to render 3D graphics, all these kind of things. On top of the Linux, interesting. That shouldn't happen. I'll just keep talking while this reloads. Thank you. I hope this doesn't happen again. That would be embarrassing. So, on top of the Linux kernel, this will load eventually. On top of the Linux kernel, we have the actual, still not the game, we have the userland libraries, like the actual game engines, Unity, Unreal Engine. We have the language-specific runtimes, like the C or the Java runtime, and we have much more concrete things like the graphics driver itself, which is also a userland library on Linux. And I hope this presentation is going to pick up soon. If not, I do have a backup. I will just restart this browser. We have all the time in the world. Goodbye. Oh, I know what's happening. So So the Linux support for this thing is a little bit experimental, because as it turns out, not many people are running Linux on ARM notebooks. And the audio driver sometimes crashes. And when audio drivers crash, Linux applications really don't like that. Yeah, so that's fun. Does anybody here like Linux driver issues? One person, great, excellent. Gotta play, okay. Wow, the spoilers are real. Oh wow, this is excellent. Talk about demos that fail, huh? Thank you. Okay, look away for a moment, please. This is fine. Here, enjoy some nature. All right, you know what? This will all make sense later. We'll just do the backup now. Hello, GPN. I'm really glad they gave me 60 minutes for this presentation. Okay, what is going on? Goodbye.
Have you tried to turn it off and on again?
I just did. Okay, cool, we're back. Let's go. Full screen, please. Thank you. So we had this smaller diagram with the x86 CPU at the bottom, Linux kernel on top, and then the base libraries, the libc and Java runtimes, the game engines, and the GPU driver. And on top of all of that, we have our actual game, Super Kitten Adventure, or whatever else your favorite game might be. So you can see we're not just talking about two components here, the hardware and the game, but rather a full stack of different components that each need their own little attention in a different way. So what we're changing in the system now, let's go through it one by one, is we're first exchanging the bottommost layer, the x86 CPU, with the ARM CPU. And what we need to, what changes here in terms of the game is ideally nothing. The game still thinks, or needs to be able to think that it's running on a regular x86 CPU. So we need some layer in between the game and our CPU to make the x86 code that the game is running, to make the x86 code that the game is running look like ARM code. And the way we do that is using a process called binary recompilation. And I want to go through that in a little bit more detail here on the next slide. So let's say you have a very small function. The details don't matter here, but it's just, this is what an assembly listening might look like for a very trivial function. You have the game instructions on the left side, and what we ideally want, and what we do, so what we ideally want at the end is we want to have an equivalent ARM assembly block that is running on our physical CPU. But the direct mapping between those two things isn't something you want to do immediately, because there's so many different pieces involved in this process. First of all, this is not what we see. What we see is just a stream of ones and zeros. It's just the raw encodings of those instructions. So to make any sense out of that, you first need to decode the instructions. You need to precisely understand the semantics, so what they do, what each of these instructions are doing, and then you need to find corresponding ARM instructions that do do the same thing as the original x86 instructions on an individual level. And then, of course, at the end of the day, you also want to make sure that everything is as small as possible. You want to have fast output assembly to make sure that you can run whatever application you're running at full speed. And so because we don't want to do this mapping one-to-one directly, we instead go through something called an intermediate representation. And what this looks like is we just decode the instructions and then map it to an internal language that's specifically designed for fax. that just captures roughly what each of these instructions are doing. So you can see here we have a push instruction. We have something called also a push instruction on our IR. When you're writing to a register, that's implemented using a store register primitive. So it blows up quite a lot, but the intent here really is just to have some more easily workable language to operate on rather than on the raw x86 instruction set itself. Using this intermediate representation, what we can now do is we can apply optimization passes, very similar like a regular compiler would. So using this, we can throw out any instructions that aren't strictly needed, combine different instructions to more optimal sets, and you can see this is already something that's much more compact, and that's much closer to what we eventually want as an output. And once we have this optimized, our intermediate representation output, that's the point where we can start actually mapping our higher-level language to actual ARM instructions. And what we get eventually is something like this. So it's much more compact than if you had gone through each instruction individually and emitted corresponding code, thanks to this intermediate representation. In practice, of course, we don't just have quite so simple code. Instead, things might blow up quite a bit if you, even if you just have a simple loop or anything or something like that. The corresponding ARM code would look something like this here. So you need to scroll a little bit. Some of this is inherent emulation overhead. This is just something we can't get rid of. Whenever we enter a function and whenever we exit a function, for example, we just need code that deals with the fact that we're emulating this thing. We're not actual code running on the CPU, but rather we are like a super lightweight sandbox in a way. And so this stuff at the very end, for example, just takes care out of jumping out of that mini sandbox. This is just inherent overhead we need to deal with. But also, there's a thing called flag handling. You can see the decrement operation that just subtracts 1, like it reduces the value of the EBX register by 1. This maps to this sub-instruction right here. You can see there's a constant 1. And we are subtracting that from the W6 register. But this is actually not all there is to it, because the CSET and the RMIF instruction around that also belong to that, and that deals with something called flag handling, because whenever we have mathematical operations that might overflow or that might turn negative, the x86 CPU would set like status flags that the application can query, and it does so unconditionally. So as part of emulation, we always need to compute this. So this is a situation where we can't just do a straightforward one-to-one instruction mapping, but rather the semantics of one instruction are so complicated that it blows up quite a lot. And these 2 extra instructions that we get here are only the bare minimum necessary in terms of the context. Actually, our optimization passes here have already thrown a lot, around 20 other instructions or something like that, just because the flag handling can be so heavy. And because it's actually rarely used or rarely needed in practice, our optimization passes here help throw out all that unneeded complexity. So yeah. In terms of the engineering effort that goes into this, so this is already a lot of inherent complexity just architecturally, what kind of design and like code modules we need to write in the software, but also the pure scope of the x86 instruction set is quite massive. So depending on how you count, there's between 1,000 and 6,000 different instructions encodings that we need to deal with. And as you might imagine, it takes quite a while to get through every single one of these. And this is also why we really need this intermediate representation, because having bespoke optimization rules for each of those 6,000 instruction patterns would just not be tenable in the long run. FEX also deals with vectorization extensions, such as SSE, which some of you might know, but also more recent extensions like AVX. FEX, as a matter of fact, was one of the first x86 on ARM emulation engines that supported AVX. I think, if I recall correctly, Apple with their Rosetta layer kind of were neck on neck with us. Microsoft took a little bit longer, but yeah, we were among the first, and I think that actually speaks a lot because we're an open source project and we can still keep up, maybe due to external influences, as we will see in a later slide as well. Yeah, no talk about x86 emulation, though, would be complete without a mention of the memory models. So if any of you have heard the term TSO before, this is where that comes in. And for those who haven't heard about it yet, let me give you a simple example. So let's assume we have an application that tries to compute a result using multi-threading. So it just has one main thread in the application that initializes the result to zero and keeps some sort of done indicator, and then just sleeps until another thread toggles that done flag to indicate that the result has been computed. And only once that is done, it tries to print the result. The second thread now will just compute that result, compute 42, as you might know, that takes a while. And once that is complete, it will toggle the flag to 1 so that the thread on the left wakes up. Now, there's all sorts of technicalities that I'm skipping over here, like compiler optimizations and whatnot, but like take this code at face value and just assume it's the correct thing. Now, what might you expect to be printed in that case? If you're computing the 42 and the thread's writing the result, you might expect that the thread on the left just writes 42. And on x86, you would be right. And this is exactly what would be happening. But on ARM, this might not always be the case. And this is exactly related to certain guarantees that these CPUs make for us by the specification. And the x86 specifications are just slightly more generous to application developers who aren't quite so careful about multi-threading issues. So what you see on the right here is exactly the order of operations that thread 1 will be observing. But on ARM, the processor has much more freedom in terms of how these operations are triggered in memory. And on ARM, you might actually see that the done flag is written before the result is assigned to the other variable. And so that would be a race condition in that case, because the while loop here would wake up before the actual result has been written, and the print statement might still write the old value. So you would, in fact, see the value 0 being printed here in some of these cases. And so our job as the emulation layer here is to make sure that every single memory operation that we translate to ARM operations adheres to these stronger guarantees that x86 makes for applications. And there's not really any silver bullet to doing this. Basically, if you basically what we have to do is we have to insert memory barriers after every load store instruction. And in some special cases, we also need to convert any memory operation into an atomic memory operation, which adds a ton of overhead to things. Basically, if you do it for full correctness sake, you would cut performance in half. So this is by far one of the biggest bottlenecks that we have in the emulation space here. And so naturally, we employ heuristics to make sure that the overhead isn't quite as bad. There are also some more modern modern extensions to the ARM instruction architecture. So, for example, a thing called LRCPC allows us to just make things a little bit more efficient in general. But also, we employ some heuristics, like, for example, local stack access, whenever an application just modifies local variables. The assumption is just that these never deal with multi-threading, which is an assumption you need to verify. But in practice, we found it holds up quite well. And so because local variable accesses are just so common, it really already helps a lot. We also have a very fun bespoke hack for Unity games, which is based on the observation that Unity games queue commands in a certain memory region called a ring buffer. And they do this in a multi-threaded way, so the Unity engine actually has synchronization primitives that rely on these strong x86 memory ordering semantics. And we found that if we just enable the expensive emulation strategy for a very specific instruction pattern, it's something like a store relative to a register by exactly 61 bytes. So as you might imagine, it's really, really specific here. We only match a couple of instructions in the entire program like that. So only for those instructions we enable the expensive emulation strategy to make this ring buffering mechanism work. And it turns out for Unity games, this is often more than enough. So for every other memory access, we can just use regular load store instructions that are fast, that are basically the happy path. And only where it's really, really needed, we need to go the laborious route. And this is a massive hack. To be clear here, like this won't work if Unity games in some other places used the strong memory model. But because the Unity is such a widely used engine, and because it works for so many games, we still consider this worthy trade-off here between accuracy and speed, because the speed difference really is massive in this case. Oh yeah, some other things that exist actually. Some ARM CPUs have built-in support for the strong x86 memory model. Apple CPUs, for example, do this notoriously. There are some trade-offs here, but as well, if you can enable this and it works in your application, it can provide a decent speed up. Yeah. So this is more or less all you need to know about the CPU emulation part of what FEX is doing. I also mentioned the next layer here, that is the Linux kernel. And again, we have a layer in the application stack, or in the software stack, that is based on the ARM architecture, but really we need to present it as in the way that the x86 application would expect the Linux kernel to work. And largely, we're talking about Linux on Linux, so it's kind of similar, but there are some small differences in terms of how the low-level interaction between applications and the kernel actually look like. So that's something we need to take care of. And then also we need to do some bookkeeping in the process, just because threads, for example, are something that FEX needs to be aware of. And also that need to be presented a little bit differently to the application. So yeah, just to give you some examples, multithreading and signaling across processes, for example, this is something that FEX just needs to hook into and like provide a small mini runtime just to make sure that they're translated properly. The file system is something, because x86 applications need to access x86 versions of their libraries. So if the game tries to load libc, we need to make sure that the game doesn't see the ARM libc, but rather it sees the x86 version of libc. And to do this, we need to hook into any file system access and redirect that into an x86 rootfs. That looks as if the application were really running on an x86 file system. And then we get the system calls that just deal with general memory management and that kind of thing. Again, this will be actually elaborated on the next slide. And then we get things like the GPU driver, which actually provide a very device-specific interface for the application, or for the userland driver specifically. So that is something that FEX needs to put a lot of effort into to make sure that the GPU driver interface also is presented as if it were an x86 interface. Yeah. So FEX sits between the ARM Linux kernel and the application to translate all of these submodules and different subsystems in a way that looks like an x86 system. And to give you a little bit of an idea of what this looks like in detail for the system call wrappers, so essentially what you will have in the game code at some point, there we go. In the game code at some point is if it's trying to do a file system read, for example, it will put the parameters to the the system call, like the file handle and the output pointer, into hello. Okay, I can't select text here. into specific CPU registers, and then it will call this syscall instruction, which triggers a transition from the application into the kernel, where the kernel will see the system call ID here in, again, a specific register, and it will trigger the behavior corresponding to that system call. Now, this is x86 code, and as we saw before, FEX will encounter this code and translate it to corresponding ARM code. So what we do for the system call instruction, well, first of all, we will convert these register assignments into similar register assignments just for the corresponding ARM CPU registers. And the system call instruction, that gets turned into a function call into a C++ function implemented by FEX. So this is an explicit exit point where we jump out of this recompiled code back into C++ code in FEX. And then we just have this small handle syscall function here, which takes the system call ID and like some context state that doesn't really matter here besides that at that point. And then we can just inspect the system call ID and toggle system call specific behavior. So when we see a file system read, we call another function, another C++ function called doRead, for example. If it's a write, we call another function. And so we're gradually getting away from these nitty-gritty low-level details and more into regular application code. This is the entire purpose here. Get away from raw assembly and make it look more like C++ code, because this can be complex logic and we want to deal with it with normal C++ code rather than writing all of it in inline assembly. Yeah, so to give you a little bit of a more concrete idea here, what these wrappers do, so when we call a doRead function, I think I can also do this. Yeah. Anyway, in this doRead wrapper, we don't do a lot because we already get the parameters from the context from the slide before. We just call the read function that calls the ultimate ARM system call. So it calls the system call for the ARM kernel. So we went through all of this effort essentially to decode the parameters, to notice that we're in a read system call, and we just dispatch this operation back to the ARM kernel interface. This is kind of what you would expect, right? You have an x86 system call, you just map it to the corresponding ARM system call. For some of these things like memory allocation, this is what mmmap does. This gets slightly more complicated because FEX needs to actually track all of the memory regions allocated by an application. So we have like a dispatch to a tracking class, which is doing more work behind the scenes. And then there's more ugly things like querying the current time of the system, which might look innocent as well. So you say, OK, we're in an x86 time query. We just call the corresponding ARM system call again. But then you notice, wait, we're actually running a 32-bit application on a 64-bit ARM system, because that's actually a detail I didn't mention so far. FEX only operates on ARM64 devices, because any high-powered device that you will buy today, that is only going to support 64-bit. So actually, if we're running a 32-bit application, we're dealing with different types, and the system call interfaces are not compatible with each other anymore. So we're actually dealing with two different structs, one being the 32-bit one and one the 64-bit one. And we need to deal with this very ugly repacking logic where we just take the results and repack them in different structures. It's not terribly difficult in terms of the actual like intellectual performance that is happening here, but it's just a lot of work, because there's again hundreds of these instructions that FEX, hundreds of these system calls that FEX needs to deal with. But yeah, luckily we've all got most of that work behind us. For most of them, it's straightforward. For others, you need these memory tracker subsystems, for example. And then there's really hairy things like forking processes, which really needs a lot of care to be taken to not cause any problems in the long run. But yeah, we're luckily past that. And yeah, I hope I didn't lose too many of you so far, because we're actually, in terms of the core infrastructure of FEX, almost done. Because yes, we have the hardware dealt with now, and we have the operating system kernel. I was mentioning the third layer, which is the base libraries, the game engine, and the GPU driver. But as it turns out, in terms of emulation, these base libraries aren't really all that different from regular game code. You can consider the game code and those base libraries as one big blob of code that just runs underneath, runs on top of all of these emulated interfaces. And there's nothing really special we need to do just to get these libraries running. And so we're actually done here at this point. So we can now draw a line here and see we have the unmodified x86 software in our program running on our shiny new ARM hardware in a x86 custom x86 disguise implemented by FEX. And this is essentially the core architecture of what we're talking about today. We can do slightly more things, though, to make it faster, because yes, this all works, and it's amazing that it does. But one thing you might quite quickly think about is, well, actually, one thing you observe in practice is that things like the GPU driver, when you're talking about Vulkan, for example, this is where most of your CPU overhead will be spent. So you will spend a lot of time just emulating this Vulkan library, which is very performance sensitive. This is really something that needs to be as fast as possible. So one trick that we found is that we can actually, since we hook into file system accesses after all, we can capture any access to the Vulkan driver by the application and inject our own little Vulkan bridge replacement there. So this completely sidesteps the x86 Vulkan driver at that point. And what it will instead do is it will call into, it will trigger a FEX-specific architecture transition, and instead of emulating the x86 driver, it will go straight to the ARM Vulkan driver that is already installed on the host system. So that way, not only do you save on translation overhead, on the time spent on recompiling the code, you also save memory, and of course, the thing that you end up running is much, much faster because you're not dealing with the instruction blowout you saw on one of the first slides before, but rather you're really just running the native code directly. And this can really make a dramatic difference in some games. There used to be one specific application, one specific game that ran at like 5 frames per second or something without this mechanism. With that mechanism, flew in 60 FPS just because you don't have all of that overhead. So that's one trick we do. We do this very selectively for the Vulkan driver and also for the OpenGL driver. There's potential for future expansion, but this is what we have today, and this is also what's making the biggest impact in that space. And one other thing that deals with the recompiler overhead specifically as well is a caching mechanism. So the idea here is that when we're running a game for the first time, you never know what kind of code is going to be executed. There are some knowns about where functions are located in the code, but generally, discovering x86 code is a surprisingly difficult problem. And so every time you start the application, you just need to recompile things from scratch, and it just really eats a lot of time. So you don't want to enter a new game area, for example, and be presented with a microstutter just because you're encountering new code that needs to be compiled on the fly. So rather what we want to do instead, we want to do this emulation, this recompilation overhead once in the beginning, in the first run of the game, and then save all of the compilation outputs to the disk so that on the second run of the game, you can just load all of this previously executed effort at startup of the game. So now you don't need to do, now you know where the code is, and you know you already have the code compiled, so you don't need to compile it when you enter the new area because it's already there. It's already on disk. You can just load it from there directly. Yeah, and with these two tricks, this is more or less where the FEX architecture is complete, and this is where we get to the demo. So I hope you're, because it's getting quite late, I know, I hope you still have some energy left for that. Do you want a demo? Can I ask again, do you want a demo? Yes! Thank you. I always wanted to do this. It's so cool. So you might be surprised or you might not be surprised because things have already gone wrong. But the clue here was this. This was supposed to be the demo anyway. So what you saw in the beginning, though, you saw it working, was that this is actually, if I exit full screen, this is not like a PowerPoint presentation, but rather an HTML page that is doing the presentation framework thingy, I don't know, that is running in Firefox as a browser. And you can actually run Firefox as an x86 application in Fex itself. And if it hadn't gone wrong before, you wouldn't even notice the difference. So what would have worked is like you get native window decorations. I mean, Firefox doesn't use native window decorations, but you get the same kind of look and feel like your normal application. And applications, it shows up in my taskbar on the right here. So this is not like a virtual box where you get a dedicated window, but rather this is just like a general application. Yeah, like a general application that you would normally run in your system. And yeah, you could have gone to the troubleshooting information, and it would have said x86 somewhere here, I think. I don't know. Yeah, but this is the ARM browser, and for different computer reasons, this says x86. So yeah, anyway. Also, I wanted to show you a shader toy, which I'm not even sure my Wi-Fi is working. So shader toy was working. I've done this presentation at Congress last year, so at the end of last year. There's a video of it proving that it used to work reliably. And again, I'm happy that today at least you got to see the first 2 slides or something of it working as well. But yeah, but this was not the full demo. I still prepared a really, really awesome demo. And yeah, so this is just proof that this is also running on an ARM64 system with this kind of hardware. So as I was saying, this is a Lenovo X13S. It's quite dated hardware by now. I don't know, 4 or 5 years old, I think. It's about as powerful, I would say, as a MacBook M1 Air. Slightly less powerful, so. But yeah, in just about a moment, hopefully, if the demo doesn't fail again, we will see something pop up. Like this. Oh yeah, and that is not gonna fly if my Wi-Fi isn't working.
Just wait a bit, it might go into offline mode.
Fingers crossed. But yeah, in the meantime, while that's starting up, I can actually talk a little bit about Steam and why Steam is a royal pain in the butt to emulate. So Steam is not just a regular like GUI application like anyone else, but it's really much more like one of those Electron applications that some of you might love or hate. It's using a thing called Chromium Embedded Framework, which is kind of the core of Electron, I would say. So all of the things you see in Steam are actually like HTML components, more or less, rendered using this Chromium Embedded Framework. It has a funky sandboxing stuff to make sure that whenever you run a game, you won't, you know what, I'm just going to turn on a hotspot. So it's using like a small sandbox based on bubble wrap that makes sure that your games don't accidentally throw up all over your file system, for example. So it contains the applications that are actually running here. There's quite a lot of complexity that goes into this thing. And this actually makes, ironically, just getting to the UI for launching your games the most complicated part, perhaps, of emulating x86 games. And yeah, so we can now launch actual games. Play anyway, thank you. And if we give it a moment, so this is the part now where it's also setting the sandbox, for example. It's launching a windowed mode because I configured it to do, because it's more handy for development. But it would also just launch just fine in full screen mode. This is a really good game, by the way. You should play it. Yooka-Laylee had a, how do you call it? Not a re-release, but like a high-definition remaster recently. Worth playing for sure. And as you can see, so we're not just like a prototype emulator or anything that runs small indie games, but this is actually able to, hopefully it doesn't crash, thank you. That is actually capable of running like full 3D games at reasonable performance. Yeah. So this, for some reason, actually always lags much more if I connect it to an external display. I don't know why that is. Like it's like I literally have it fluent on my laptop screen. Yeah, I can't show it to you. You just have to trust my word. But yeah, so this is working. Oh no. This officially stops being a presentation about x86 emulation now, and this is now the Let's Play part of the talk. So one other thing that you might have wondered about is like, hey, sure, Linux games are cool and all, but you know, I want to support game developers that support Linux, but still my most favorite game, Tunic, which is also a very cool game that you should play, unfortunately doesn't have a Linux build. What am I going to do about it? Well, you just stack the emulation layers. So what you can do, of course, well, more or less of course, is you can take facts to make your ARM CPU look like an x86 CPU, and then your virtual x86 CPU can run an x86 build of Wine or Proton. And using that, you can play Windows games on Linux on an ARM device, hopefully. Any moment now. But you know what? We're just going to head back to the presentation while that is launching, and hopefully we'll be fine. So yeah, just a little word about... There we go. OK, thank you. Right. So yeah, even that works. So this is again a Windows game running on Wine or Proton on fax at quite capable frame rates as well. This one has an FPS display right built in, and for some reason this actually works fluently. So I don't know what's going on in Ukulele, but yeah. So fax being so awesome, you might wonder, is anybody actually using it? So as a matter of fact, people have been trying to bring up Linux on Apple Silicon devices. So if you own an M1 or M2 device, this is actually something I can really recommend as a daily driver. Linux on these devices is super stable. It's a really pleasant experience, super polished, even compared to x86 laptops. Give that a try if that's interesting to you at all. They actually have a super interesting extra challenge on top of things, which is related to a thing called memory page size. Without getting into too much details, this is like a fundamental change in their hardware and makes basically any x86 software, any x86 Linux software incompatible with it without further tricks. And the trick that they came up with is stacking emulation layers. You essentially run Proton running on top of fax in a small thing called micro VM, which is essentially a user space Linux kernel that uses a different page size than your actual physical Linux kernel. And then it all works with some performance overhead, but you can get it working. And yeah, they spent so much work on making this setup as smooth as possible, and huge props to them for actually making and pulling that off. Because at the end of the day, you just install it from their repositories, and it just starts Steam without you don't have to worry about it, mess with it. It just works. Parallels Desktop is using fax for something. They credited us in a blog post, and I think some of their x86 virtualization work factored in our recompiler work, but they didn't elaborate on what exactly is going on there. But it's quite nice that apparently our open source code is usable enough and modular enough to be reused in another contexts than ours. Crossover, the professional offering behind Wine, they started integrating FACS for supporting Windows applications. Like, they wrote a whole blog post about it that you can read here with some examples. I think Cyberpunk, for example, if you were still thinking that we only support small niche indie games, like Cyberpunk 2077 is running in FACS using this kind of approach, for example, running at quite capable frame rates. And yeah, you might have also seen the Steam Frame, which is a hardware device coming up by developed by Valve, which is coming up this year, as something that is quite heavily based on FACS for game support, because this is also an ARM-based platform, and this is probably also the part where I can disclose. Valve actually has been generally paying me and other people, other developers as contractors to make FACS better than it is today. And without them, this has been going on for years, so without them, none of this would have been possible. So huge props and thank you to them at this point as well. I already talked a little bit about Windows by showing you Tunic running. So yeah, we can see if you have Puppy Simulator X, because obviously, anyway, this can run on a x86 build of Wine as a sort of runtime, which will then also bundle a set of x86 Windows libraries, which will in turn be based on x86 Linux libraries, which in turn will run on the ARM system underneath, so the hardware, the Linux kernel, and the base libraries, thanks to FACS, the recompiler, and the kernel compatibility layer as a disguise in the middle. So this is just the stack that we were seeing before, but there's actually a slightly more intelligent way. No, actually a massive layer, I shouldn't understate that. There's a massive simplification we can make to this architecture diagram. And this is using a technique called ARM64EC. But see, the general idea is, well, we have Wine as an open source project, so why are we compiling it to x86 in the first place? There's not really, I mean, there's reasons for that, but naively you might expect we could just use an ARM build. So, as a matter of fact, this is what we can do. If you adapt the Wine core accordingly, it can be an ARM application that you run in the system. So for Wine itself, you already save the recompilation time overhead, the memory usage overhead, and just make it faster in general. But then also there's a tweak which was invented by Microsoft themselves for their emulation solution, which is ARM64EC. And what that is, it's a custom calling convention that allows you to compile ARM code in a way that is very, very easily callable from recompiled x86 code. So you remember the inherent recompilation overhead in the beginning, where we need to exit out of recompiled code when we want to call C++ functions and FACS. With ARM64EC, most of that goes away, and you can almost directly call into your native code again. And what that allows you to do is it allows you to move the It allows you to move this recompiler block up several layers in the stack. And instead of recompiling the whole world on top of it, you can now recompile your Windows libraries, which Microsoft has the source code to after all. Instead of compiling them to x86, they can compile those to this ARM64EC calling convention. And when you do that, there's no reason they need to use the x86 libraries, Linux libraries underneath. They can just use the native ARM libraries. Once you use the native ARM Linux libraries, you don't need a kernel compatibility layer anymore. So your whole diagram condenses down into these tiny 4 little layers, and all of a sudden you only have the application itself remaining that needs to go through the emulator, and it's talking to the actual Windows libraries as a emulation friendly recompilation of what they used to be. And so we like to go, so if you want to contrast these two architectures, the one is really x86 Wine running in FACS. And just to contrast the two, we came up with the term Wine on ARM. Why the name? Because it shortens to WA, like Windows on ARM, so it's the analogy here. It's essentially just Wine running directly on ARM, and because it's really inspired by the Microsoft architecture, it really makes sense to just use the same acronym, so yeah. FACS supports both operations, but like it's a different deployment target, so to speak, so you need to explicitly compile FACS for one of those different modes, or use both if you want to freely switch between them. Yeah, it's a much simpler stack because there's fewer components involved. You need to spend less memory overhead. You don't need to recompile as many things. And it's just generally faster because of some extra tweaks. You can read a lot more about this in detail by one of the core architects that designed the system at Microsoft. So if you're at all interested in what goes on there, I really recommend checking out this link. And yeah, just really briefly, what's next? Well, we want to make sure that FACS runs as fluent as possible for anybody trying it out, especially with the Steam Frame launch coming up. We want to have better performance, lower memory usage. We want to have better compatibility. But generally, I think we're in a quite good position because so few people have heard about the project so far. I think expectations might actually be quite low. And I think people might be surprised quite pleasantly about just how well it already is working. But yeah, if you have an ARM Linux device at home and want to give it a try, feel free to, and let us know how it's working so we can end up making it better. I wanted to say other things, but I'm blanking, and also I'm running out of time, so I'm just going to move to the last slide now, where I'm summing up again everything that we've been talking about. And that's all I have, and maybe we have a couple of minutes left for questions. Thank you.
Okay, a lot of questions.
I have two questions. First would be, correct me if I'm wrong, but I think Linux on x86 has multiple calling conventions, and do you support all of them? And second would be, do you have trouble with detecting already compiled x86 code because of DRM solutions?
So with your what solutions?
DRM, Digital Rights Management.
Right. So the first question regarding multiple calling conventions, FACS is actually agnostic to calling conventions because at the end of the day, you're just passing registers across, like function boundaries aren't real. So, because at the end of the day, you're just preparing registers in a specific state, and then you're just changing the position in your program where the CPU is executing code from. That's what a function call is at the end of the day, and everything around that, a calling convention, is just that. It's a convention, but FACS is completely oblivious to what's happening there. It doesn't need to care because it's just mapping register assignments to register assignments and jumps to jumps. About DRM schemes, there's a lot of technical stuff going on there that I don't think we have the time to go into, but we support whatever we can. We're just naturally limited also by what, for example, Proton itself supports on x86 systems themselves, even without FACS involved. But yeah, find me later if you want to know details.
Yeah, I actually had a similar question to the DRM one. Just can you deal with...
Where's the question, actually?
Sorry? Yeah. Like, can your recompiler deal with self-modifying code or unpackers or stuff, right? Because
right,
that sounds like a cursed problem.
Self-modifying code is actually not that bad. There are certain constraints around it, but because self-modifying code is often signaled quite clearly to the Linux kernel by changing by making memory explicitly non-executable, then patching it, then making it executable. So FACS has a few easy detection points for that, so to speak, but there's also more, I forgot what we call it, but there's like a more accurate, more stronger, more accurate mode where we more aggressively detect when code has been modified. So yeah, long story short, we do support self-modifying code.
So you mentioned earlier that, you mentioned earlier that the Apple CPUs actually support the x86 memory model natively. Do you know if the Asahi Linux people have been able to use that instead of having to emulate the memory model?
Yeah, so SI exposes a like bespoke kernel interface for this, and FEX actually picks that up and enables it by default, I think, when it's supported. So yeah, there's a bit of trade-off actually in using this flag because so especially with the one on ARM approach, there's actually quite a lot of non-recompiled code in the entire emulated process. So there's actually a trade-off here, where you make the emulated code faster, but because enabling this mode carries some performance overhead, I think around 20% or something, it might be wrong, but it's not insignificant. So you make the recompiled code faster, the emulated code faster, but all your native code runs slower, so it's not quite clear where the trade-off is always.
If you don't translate it one-to-one, but you look at the context, I imagine you need to like cache the instructions somehow, so that you can look at the context. How do you decide how much context you have to look at and how much is it generally?
So we don't need to cache anything for this specifically, but we do compile. So these in recompilers, you talk about basic blocks, and these basic blocks usually just cover 3 to 5 instructions, for example, to give you an order of magnitude. But FEX actually compiles larger chunks of blocks, up to 5,000, as a matter of fact. Usually in practice, fewer than that, of course. But yeah, we, for example, with the loops in particular, it's just really useful to compile the whole loop body as a whole, because that's really where the flag optimizations really shine, because now the loop counter, for example, doesn't need to carry all of these flag computation overhead, but instead we can reason more or less globally about the whole loop, and we can optimize a lot out of that. Does that answer the question? Yeah. Perfect.
I have 2 questions. The first one's, did you try to use or...
Sorry, who's asking? There we go.
Yeah. I have 2 questions actually. Like, did you already try to use like professional software, for example, CAD software, or like, software for industrial automation, which are, in the back end, oftentimes like really, really integrated? And the second question, Apple used before x86 architecture, they used PowerPC, and it's also RISC-based. Is it easier to make an emulator like from RISC to RISC than from CISC to RISC?
For the first question, I haven't personally tried like CAD software, for example. I would imagine them to not have too much trouble, actually. I think the legacy mostly comes from things like GPU access, where they use quite a few bespoke features, and you might have trouble finding an ARM platform that supports the right feature set there. So I think that would be the biggest hurdle. But in terms of the CPU emulation, or maybe even the system call stuff that they use, if it's supported by Wine, of course, in the first place, right? Again, if like your x86 platform already can't run these applications, which are probably Windows specific as well. If Wine on x86 can't even do that, it's not going to do that with FEX in the mix. But in principle, I would expect them to work. If they don't, and you try it out and you find that they don't, feel free to let us know. And in terms of emulating different CPU architectures, I think it doesn't really make that much of a difference at the end of the day. Yeah, sure, like x86 is a pain to emulate properly and like to cover all of these instruction sets. But if at the end of the day, that's a matter of spending the time and effort down to it. But the core engineering challenge here is also just to make it fast, right? And you have that challenge regardless of which architectures you're translating to which other ones.